Hi everyone, happy Wednesday. A couple of course reminders, homework 3 is due tonight, optional homework 4 is out today. And also hopefully you've been getting started on your projects. The project milestone is due in 2 weeks on Wednesday. Again, we're similar to the proposals. We're going to be grading them pretty lightly. Really, the goal is to be able to give you feedback on your project and help you keep on track in terms of making progress towards the end. So for today, we're going to recap quickly Monday's lecture on the basics of meta-RL. Then we're going to talk a lot about learning how to explore. This will be first just talking about end-to-end optimization of exploration strategies, and then talking about some alternative strategies that address some of the shortcomings of end-to-end optimization, and then talking about an approach that tries to get kind of the best of both worlds. Meta-RL and learning to explore is the focus of homework 4, and so this lecture will be probably super useful for that homework. And then the goals of the lecture are to understand the challenges of end-to-end optimization of exploration, understand the basics of using some alternative strategies, and then also be able to understand and implement the last approach that decouples exploration and exploitation. Cool. So to recap meta-RL and what we talked about last time, we want to be able to learn how to solve a maze, for example, or solve a new task quickly. And the way that we do this is we learn how to learn many different mazes or many different meta-training tasks, and then use this to try to quickly solve a new task where we explore in a new maze. This exploration constitutes our training data set, and then we use this to solve a task and acquire a policy that can go straight to the goal of the maze. We also talked about the problem of meta-RL kind of more abstractly, where we want to be able to take some experience in a task and use that to form a policy that maps from states to actions that can maximize reward for that given task. And the way that we do this is we collect a data set of data sets, one data set for each task or one replay buffer for each task, and we use this to learn how to quickly solve one of the tasks in our task distribution so that we can hopefully generalize to a new task. And so there are two aspects of the meta-RL problem. One is picking a good function f that can learn how to adapt from data. And the other is figuring out how to actually go about collecting and exploring in the task. And the second part is essentially the problem of learning how to explore. And this is exactly what we'll be focusing on in this lecture. We sort of swept this under the rug on Monday, and there are actually circumstances where exploration is quite non-trivial, and you want to learn a more sophisticated exploration strategy than where you're actually optimizing for the exploration strategy rather than something more arbitrary. Cool. And then in today's lecture, we're going to be focusing on black box meta-RL methods. Last time we also talked about optimization-based meta-RL, but here we're really going to be focusing on black box methods. The way that we saw black box methods working is you have, for example, a recurrent neural network that takes as input the experience so far and uses that to infer what a good action is for solving the task. And you could think of dtrain as essentially all of your experience up until the current time step and your query set as the current time step. And you're going to be optimizing this network for many different sizes of support sets. For the purpose of this lecture, we're going to call our initial episodes exploration episodes and our later episodes execution episodes. They don't necessarily need to have a very hard breakdown of like one episode for exploration and one episode for execution, but it'll be helpful just in terms of understanding. It'll be helpful to kind of break these into two different parts of the problem for understanding some of the challenges that come up when you learn how to explore. Also, sometimes in the exploration episode, sometimes you actually don't really care about how the reward that the policy is achieving during the exploration episode. Oftentimes you only care about that during the execution episode. Although in some circumstances, you might also want your exploration episode not to like jump off a cliff, for example. In terms of black box approaches, they're very general and expressive. There's a variety of design choices in the architecture, but they can be difficult to optimize, like we talked a little bit about on Monday. We also talked about how these methods will inherit the sample efficiency of their outer RL optimizer. Cool. So that's a recap of some of the concepts that we covered on Monday. Now we're going to be talking about learning how to explore. And I'd like to start this by taking a step back and thinking about reinforcement learning in general. And oftentimes in reinforcement learning, we'll use a number of different exploration strategies. Maybe we will try to maximize the entropy of our policy and do more random things. There's also exploration strategies known as epsilon greedy, where with some probability you take a random action, and with the rest of your probability you take the action according to your policy. And these exploration strategies are very naive, and we're actually using the same exploration strategies for solving a wide range of problems. And if we take a step back, it seems a little bit silly to be thinking about using the same exploration approach for learning to navigate an environment and the same exploration approach for making recommendations to users, for learning a policy for computer system caching, or physically operating a robot. And essentially in reinforcement learning, the way that we approach exploration is we have a single strategy like epsilon greedy, and we apply that to all of these kinds of problems. And that seems a little bit silly because you would expect that in a lot of these different applications, you want strategies that are kind of targeting aspects of that problem. So for example, in navigation, we want exploration strategies that try to reach different parts of the environment. In recommender systems, we may want to kind of have approaches that are targeted towards particular users and treat different users differently. In terms of physically operating a tool or a machine, there are probably certain things that we want to try and certain things that are irrelevant and won't be helpful, like walking to another room probably won't be helpful in terms of exploration for that particular tool or machine. And so in some ways, the idea behind meta reinforcement learning is trying to learn exploration strategies based on other tasks in that particular domain in order to be able to in order to explore in a much more targeted way for a particular domain. And so if these algorithms are very effective, we may be able to get exploration strategies that are very targeted and that are some more domain specific than things like epsilon greedy. Okay. So in terms of the algorithms that we'll think about, I want to think about them in the context of an example. And I think that this should help give across some of the intuition behind the algorithms. And the example that we'll consider is as follows. So we have some agent. This is what's choosing to take actions in the environment. And there are a number of different hallways in the environment. And different tasks correspond to navigating to the end of one of the hallways and receiving a reward at the end of the hallway. And so for one task, maybe the goal is to go to the end of hallway 2 and collect a reward. For another task, the goal is to go to hallway K and collect a reward, and so forth. So this is kind of the basic version of the setup. And if you were to learn how to explore, you would imagine that you might want to kind of explore the ends of different hallways. We're going to add one more bit to this environment, which is that on the ground, there's also some paper that has instructions on a hallway that is on essentially where the robot should go for the current task. Cool. And so this is also kind of illustrated in a much more basic way right here as well. Does anyone have thoughts on what some strategies are for exploring and learning a new task? Yeah? Yeah, so one thing that you could do is you could try to find the sheet of paper on the ground, read it, use that to figure out where to go. And then if you can effectively read what's on the paper, then you could just go there directly. And then another strategy would be, if you don't know how to read, you could try to basically just go down all of the hallways until you find the hallway that gives you a reward. So these are two effective strategies. And those are, I think, the only two effective strategies for solving this problem. If you don't learn to go to the end of the hallways or you don't learn how to read, then you probably won't be able to learn the task. Okay, so we'll be considering this example throughout, and it'll be useful for understanding different approaches. So now the first approach for learning how to explore is just to try to optimize for exploration and task execution end-to-end with respect to the reward of solving the task. This is essentially what we saw in the lecture on Monday, where we trained a big recurrent neural network to be able to do both exploration and execution for the task. And we could train it with something like Q-learning or something like policy gradients. If we train it like with policy gradients, we'll get an objective that looks something like this. And essentially what this is going to be trying to doing is your policy is going to need to both explore as well as use the exploration data in order to solve the task. And so if we think about the meta training process, it's going to be collecting episodes and trying to learn how to explore and solve tasks. And so say during meta training, maybe it collects it's trying to learn how to explore and solve the task distribution. Maybe it collects a trajectory that looks like this, that goes to maybe even the correct hallway and gets a reward. An episode that looks like this is great in the sense that it's going to get positive reward for the current task. But it's not actually going to be able to learn exploration from this trajectory. Because it hasn't, detrain isn't really going to say anything about what task is or isn't the case until it gets to the very end. And so as a result, even though it's giving some positive reward for the task, it's going to be fairly difficult to use a trajectory like this to figure out how to both explore and solve the task. Now, another trajectory that we might consider is maybe something like this, where the agent kind of goes to the end of one hallway and then goes to this one. This trajectory will get positive reward again, and it's actually also going to get positive reward for it's going to get positive reward that will help it learn an exploration strategy of going to different hallways. And so in general, this trajectory will probably be much more helpful than the green trajectory, because it can learn an exploration strategy, which is if you see a negative reward, then you should go to a different hallway. So this will be helpful, although it's going to be helpful for learning a suboptimal strategy, because the optimal strategy would be to read the instructions first and then go to the correct hallway. And then lastly, say that you have a trajectory that looks like this, where the agent actually does go and reads the instructions. And then maybe after it reads the instructions, it does some random stuff. An episode like this is good in the sense that it is actually showing some exploratory behavior that's informative for the task. However, it's not going to be able to use this experience in a meaningful way, because it's still going to get a reward of 0 for this experience. And so in this last case, it has good exploratory behavior, but that is not going to get any reward for this exploratory behavior. And as a result, the only in terms of learning the optimal strategy, the only kinds of trajectories that will be helpful for learning is if it actually first goes to the instructions and then goes to the correct hallway. And so this illustrates the challenge of learning exploration and exploitation end-to-end, which is that if you're trying to learn both of them at the same time, you really need trajectories that do both exploration and execution of the task in order to get good signal for how to do exploration and execution together. And if you have a trajectory that does only one of them, that isn't going to help you very well to essentially learn how to solve tasks in your task distribution. Any questions about this? Yeah.
Might be silly, but why can't you just reward the agent for looking at the instructions regardless of what they think?
Yeah, so the question is, can you just reward the agent for like looking at the instructions regardless of what it does after that? And that's something that you can definitely do. If you know what a good exploration strategy is, then you could essentially change the rewards during meta training to encourage it to kind of shape its exploration behavior. And that will encourage it, that will make the problem much easier, and that will encourage it to actually do that behavior. Note that you do need to have some sort of domain-specific information in order to do that, and you need to know what a good exploration strategy is in order to provide that kind of reward shaping. If you can do that, then that will help solve the problem. If you don't know that information, then you're still kind of stuck with the challenge of this sort of end-to-end optimization. Cool. So to summarize kind of this sort of end-to-end approach, it's very simple, and it in principle will lead to the optimal strategy if you give it enough data and it eventually kind of explores the correct exploration and execution strategy. The downside is that it's a very challenging optimization process, especially when exploration is difficult, because it needs to kind of figure out that exploration strategy in conjunction with solving the task. We can also look at another example of kind of a hard exploration meta-RL problem. And we can see how this problem arises in that problem as well. So say that we want our robot to be able to cook us a meal, which would be nice. And the meta training tasks correspond to cooking in a number of previous kitchens. And then our goal is for the robot to be able to cook us a meal in our kitchen, which is a new kitchen. In order to cook, you need to find ingredients for the meal, and then you also need to use those ingredients to make the meal. And so you can think of exploration as finding the ingredients, and execution is actually using those ingredients to cook. And one of the things that's difficult about end-to-end optimization is you have a kind of a chicken and egg problem between learning how to explore and learning how to solve the task. And if you say, for example, you haven't yet learned how to explore, you don't know how to find ingredients, then if you don't have ingredients, then you can't learn how to cook. And likewise, if you haven't yet learned how to cook, then you're not going to get any reward for finding the ingredients. And this is the second example is just like this case, where if you haven't yet learned how to read instructions and go to the correct goal, then you're not going to get any reward for looking at the instructions. And so essentially you have this coupling problem where learning how to explore and learning how to solve tasks depend on one another. And if you try to optimize for these end-to-end, this can lead to poor local optimum, like the approach of exploring different hallways. It can also lead to very poor sample efficiency because you need a lot more data in order to happen upon the strategy that explores and solves the task. Cool. So that's the gist of why end-to-end training is hard. Kind of in the rest of this lecture, we'll talk about alternative strategies that essentially try to bypass the difficulty of this end-to-end optimization. Do folks understand why end-to-end optimization is hard? Cool. I see nods. Okay. So the second solution that we will look at is to try to leverage alternative exploration strategies. And instead of trying to explicitly learn an exploration strategy that is kind of the best approach for trying to figure out what the task is, we're going to leverage alternative strategies that might help us figure out what the task is. They might be suboptimal strategies, but they're going to be easier to use and optimize for than the end-to-end approach. Cool. So the first thing that we'll consider is to use posterior sampling, which is also known as Thompson sampling. And at a high level, the way that this is going to work is I'll erase kind of these here. The way this is going to work is we're going to learn how to solve each of the tasks. So we'll learn how to navigate to the end of hallways. And then we'll learn how to solve the task. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And then we'll learn how to navigate to the end of hallways. And we're going to maintain a belief about what we think the task is and sample from kind of our belief or sample from our distribution of what we think the task is. And so what we can do is we can say that we have learned that the task corresponded to going to different hallways. Then we will start by kind of having a fairly uniform prior over tasks. We'll sample from this to kind of pick a particular task that we might want to do. So maybe we'll sample task 2 to start. Then we will execute our policy for that task, which will go to there. We'll then see that we don't get a positive reward from this. Then we will update our kind of belief over the task, given the experience that we've seen so far. We'll sample a new task from our updated belief. This new distribution is going to be everything but this task right here. And we'll then, again, pick a different task and execute for that. So maybe we'll sample this task. And then we will get a positive reward here. We'll then kind of, again, update our belief over the task, given the experience we have so far. And once we see a positive reward here, our distribution over what we think the task is going to be much narrower. We'll know that the task is to go to this hallway, and that we should kind of, from there on forward, just always go to this hallway. And so this is referred to as posterior sampling, in the sense that you kind of maintain a kind of posterior distribution over what you think the task is, and then you act according to that distribution. And so kind of more specifically what this would look like is you first learn how to solve and collect data for all of the training tasks. This will be independent of learning how to explore. Then you'll form a representation of each task. This will be captured by this variable z, and we'll learn a policy conditioned on that representation of the task. And so, for example, this z, it could be like a one-hot vector of like task 1, task 2, task 3. It could also be a more continuous representation. And then once we learn this representation of task, we can then learn how to infer a distribution over the current task. And so we'll learn both a kind of a marginal distribution over the task, which is P of z, as well as a distribution Q that is trying to understand the distribution of the task given the evidence I've seen so far. And then lastly, once we have a policy conditioned on our task representation, as well as a kind of a distribution over what we think the task is, then we can do this approach where we alternate between sampling from our current distribution over the task and sampling from the policy for that task. And this is what's known as posterior sampling. Yeah?
I'm wondering what, like, step 1 seems like a really tall ask of whatever model we have, but to be able to solve and plug in for all of the training tasks just seems pretty, like, infeasible to a lot of places.
Yeah, so there's a few different ways that you can approach that. I guess I can talk concretely about how we're essentially going to do task like step 1 and 2. And in particular, I mean, in some ways you have to, like if you aren't able to solve the training tasks at all, then you're kind of out of luck. One of the things that's nice is if you do have a shaped reward for your tasks, then it will be easier to learn those tasks, whereas oftentimes you might not have a shaped reward for the exploration strategy. And so the way that this can work in practice is you could essentially do this with a kind of a particular form of a black box architecture where you learn a policy that is still takes the kind of standard form of conditioning on the current state and your training data and outputs an action. One thing that will make this step easier is, in this case, we're going to use an off-policy approach to learning the training tasks. And we'll maintain a replay buffer, a data set for each of our tasks. And once we do that and we sample detrain from that replay buffer, that buffer will contain some trajectories that hopefully eventually have actually figured out, or some trajectories that do actually solve the task. And if you condition on that trajectory in dtrain, then it's pretty easy to identify what the task is from that trajectory. And so I guess the short answer to your question is that you do need to be able to solve the training tasks in some sense. And once you do solve the training tasks, it isn't too hard to learn an architecture like this. Cool. So in terms of these first two steps, we'll learn this policy like this. One thing that's important about this architecture is that we're going to be having this intermediate representation Z that is kind of only takes as input the training data. And as a result, this means that the ZI is going to be capturing information about the task and information about the task that's needed in order to learn the policy in the critic. Yeah?
So we had to optimize at this lower bound in this case, but most evidence in this case is a trajectory on the or maybe a little bit, maybe one or two steps ahead. I won't actually be formulating an evidence lower bound, although you can actually connect this to a variational approach. You can think about the evidence as maximizing reward. I can maybe also get back to that after we finish kind of explaining the details of the last two steps. Okay, so now we've gotten what steps 1 and 2. We have a representation of the task, and we also have a task condition policy. One thing we do not yet have is this distribution over the task. And so we need to essentially impose a distribution somehow on our task variable. And the way that we can do this is actually quite similar to some of the things that we saw earlier in Bayesian meta-learning, where we, instead of having a model deterministically output Z, it's going to output a mean and a variance over Z. And you'll include a term in your objective that encourages that mean and variance to be, essentially the distribution over that variable to be a Gaussian distribution. And so you can do this again with kind of a KL divergence term that encourages the distribution over your task to follow a standard Gaussian distribution. And then the complete objective of what you're going to be doing here is you'll have one model that takes as input dtrain and outputs kind of a mean and a variance over your task variable. So this will be kind of Q of Z given dtrain. And you'll also have another model that takes as input a particular sample Z and outputs and gives you a policy for that particular task. And the objective for learning these two models is to maximize reward across all of the tasks, and also to encourage this to actually represent a distribution rather than being like a deterministic model. And this will give you, essentially exactly what we wanted here, which was kind of a posterior distribution over the task given the data set, as well as a policy that solves the task. Yeah. Is that bottom line it gets penalized like further digits away from the normal?
Yeah, exactly. So the KL divergence term is going to penalize it if it's further away from the normal distribution. One of the things that's really important about having this term is that one thing this model could do is it could just set, it could say that like, oh, I just want it to be deterministic and set the noise to be 0, for example. If it does this, then this is a problem because then when you try to like go and sample a task, it's just going to give you a single number rather than a distribution over what the task might be. It's also important to do something like this because we also want to start with some prior distribution over our tasks. And by by regularizing the distribution to this standard Gaussian distribution, this prior distribution will now just be a standard Gaussian distribution. And so when we don't have any evidence about the training data set, we can sample from the standard Gaussian, and that will represent a reasonable distribution over our tasks. You can also think about the second term as what's known as a information bottleneck. It's going to essentially encourage this task variable to carry less information about the training data than it only carry the information that's needed. But you can also just think about it as essentially just imposing a distribution over your task variable rather than having it be a deterministic model. Cool, and then getting back to the evidence lower bound question, I think that there is a way to formulate this as optimizing an evidence lower bound. It looks a lot like a variational autoencoder objective that you, as you might notice, where your z corresponds to your latent variable, and then you're trying to maximize reward. So your evidence would be, it's a little bit more complicated to actually derive the evidence lower bound because you need to actually think about reward, maximizing reward as actually maximizing likelihood in a graphical model. And there's actually a lot more formalism if you want to try to do that. So it gets fairly complicated, and it's kind of beyond the scope of what we'll cover today. Yeah?
In the context of learning to explore a maze, for example, as we were seeing before, is this assuming that we have access to tasks where the task is all possible positions of the target, or is this kind of hoping to generalize across positions of the target through like embedding of the latent variable?
Yeah, so you're asking basically, does this assume access to kind of some low-dimensional representation of the task, or are you hoping to try to generalize?
Because it is kind of a discrete distribution of our tasks.
Yeah, exactly. So by conditioning it on, by trying to infer z, this latent variable based on the training data, we are hoping to generalize potentially. And this is going to kind of represent, z is going to be a continuous variable, and so it's going to represent a more continuous distribution over tasks. And so in principle, this should be able to generalize to new tasks if your task distribution is sampled densely enough, if you have enough training tasks, basically. And so in this approach, kind of, when I was initially explaining this, I was just talking about these kind of task IDs potentially. But by actually using this task variable, you should actually be able to generalize. Whereas if you only use the task IDs, you wouldn't be able to generalize to new tasks. Okay, so to summarize, we're learning a representation of the task, a policy that conditions on that task, and then doing this form of posterior sampling in order to solve the task. As an example of what this looks like, in an example that's actually fairly similar to the mazes, is that say different tasks correspond to these blue circles, and the correct task is this dark blue circle, then what it will actually do in practice is you first sample from z, and then run your policy for that sample. And then once you do that 4 times, you'll get these 4 trajectories. And you see that it's kind of sampling from the distribution of tasks. Then once you have this experience, you can then condition your estimate of your distribution of z on that experience. And then you'll collect these lighter purple trajectories that explore in parts of the space that are not previously covered from your data. And then you'll notice that one of the trajectories here actually does go to the goal and would get a positive reward. And so once you have this experience, then it can essentially, for the future trajectories shown in orange, it'll now just go directly to the goal because it's figured out what the task is. Okay, yeah?
So in the middle column, why does conditioning on your past trajectory make you sample tasks that you don't already have examples of?
Yeah, so you're asking, why does conditioning on your past experience encourage you to visit tasks that you haven't visited before? Yeah, and so The reason why that's the case is that when you train a model to infer the task from data, if it was given data that that is doing like other tasks, then that's going to help it. Then basically, that's going to help it understand what the task is. And because we're training this encoder both for the KL divergence term, but also for the reward, when you essentially say that when you're optimizing this, you're optimizing for hallway 4, then if you condition this on data from hallway 1, then it doesn't know exactly what the task is, but it knows basically that if it wants to maximize reward, it shouldn't go to hallway 1.
So it's pushing down the beliefs of the ones that it's already visited because
It basically, the policy won't get reward for that, and so it should push down those probabilities. Good question. Yeah.
this seems like taking a piece of the cross entity because they're like when you're kind of like pushing up the probability of like projecting more take and then like reduce probability to more take.
Yes. The question is, it seems kind of like cross-entropy method. One thing that's different from cross-entropy method is that if you're getting 0 reward for these, cross-entropy method is going to try to take the best ones, and there aren't any good ones in the sample. And so it probably won't do very well if it's not going to know that it should try other things. The last step is a lot like cross-entropy method, where once you do actually have some good samples, it's going to sample more from that. But this is actually more powerful than a cross-entropy method because it has this ability to reason about uncertainty over the task, even given negative data.
Would it be a lot more computationally?
So the question is, can you use this for planning? Being able to estimate this posterior is difficult in general. And so if you can represent that posterior during planning, then you should definitely use it. In practice, having access to it, you have to learn it in some way. And this is one way to learn it. But in planning, we often don't have access to it. Yeah.
And PZ, you just assume that is normal, or like that is a uniform across all of the time?
PZ is going to be our prior. And so if we use a KL divergence to a standard Gaussian distribution, then P of Z will just be the standard Gaussian. Cool. So now a question for you. In what situations might this approach do poorly? Yeah.
When you posterior on the side of calibrated, do you then
Yeah, so if your posterior is not very good, then this is going to do very poorly. What if you have a very good posterior? Are there scenarios where you have a great posterior that's very accurate, but this still might be a bad strategy? Yeah.
you have like super sparse?
You have very sparse rewards. Yes, although I guess it kind of, if you have a couple tasks and you can like explore those, then sparse rewards will still be okay. Any thoughts on kind of task distributions or problems where this would be very inefficient? Yeah?
You can't gain more information from observing the trajectories, which means like the prior distribution and the posterior distribution have the same kind of information.
So if you don't gain a lot of information from the trajectories, and in particular if you don't get a lot of information from which trajectories? Yeah?
What if you have two solutions and it encounters one which has like a somewhat like decent reward and the other one with no reward? If you're unlucky, the sample will not be just refitting in uniform. Gaussian gonna go into that one, you're probably not gonna fit a multimodal one. So you might only do resampling on the decent reward and never see the reward.
Yeah, so if you have a multimodal distribution, it might be difficult to kind of represent the multiple modes, and it might just like pick one of them, which would do poorly. Good. Any other thoughts? Any thoughts on kind of this example and how well posterior sampling would do here? Yeah.
Doesn't really help us in this example very much. And so I think you have a trajectory that they did learn how to read, but then it didn't get any reward for it. The posterior sampling method wouldn't update the belief.
Yeah, so one thing that it's not going to do in this example is it's not going to learn how to read. It's just going to kind of try all the tasks. And so this will be a suboptimal exploration strategy because it takes a lot longer to like try the tasks exhaustively than to just read and then figure out what the task is from there. And one scenario in which this is like particularly bad is if your hallways are super long, then like exploring all the hallways is going to take a lot of time in comparison to just trying to read the instructions. And the reason why it doesn't read the instructions is that reading the instructions isn't actually part of solving any of the tasks. It just tries to iteratively solve the tasks. It doesn't try to actually see if there's any information in the environment that will actually help it understand what the task is. That's kind of independent from actually solving the task. Yeah?
One quick question, but if we were to read, wouldn't that give us complete information about, Q and psi would be like fully determined by you, which is how one peak? If that information was contained somewhere in the trajectory, but it's not contained because it wouldn't be okay.
Yeah, so if like the instructions are actually part of the trajectory and you actually see that, then it will actually learn to kind of collapse its posterior down to the correct task, but it's not going to actually go and see that. It's not going to go out of its way to go see the instructions if that's not part of actually like getting reward for the task. And so, it's not going to essentially go out of its way to find that information because it's just sampling from tasks and sampling from the policy for that task. And so if, for example, you have your goals are really far away and these instructions or a sign on the wall tells you exactly what to do, then it's not going to actually go seek out that information. Yeah?
Does it have to learn how to read? Or does it think already know? Does it
you're asking, does it have to learn how to read or does it already know how to read? I guess there are different variants of the problem. You could have one where if it's goes here, it is told directly 1, 2, 3, 4, 5, or something where it goes here and it gets an image and it has to learn how to read the text and solve a math problem and figure out what the number is. In both cases, it's not going to actually go here. Posterior sampling approaches will just try to sample tasks and solve tasks. And so the reason why I bring this up is that this approach is a lot better than end-to-end optimization in that it's a lot easier to ultimately figure out how to solve the tasks. The downside is that it may end up with exploration strategies that are very suboptimal. So in some cases, the strategy will be fine. In other cases, it might be arbitrarily bad, like if the hallways are infinitely long, for example. Another example of something that would be better than this approach right here is instead of kind of going to each of those, if it first went here and then kind of walked around the circle, then it could actually figure out what the task is in just a single episode rather than requiring a lot of episodes to explore. And that's even without a sign. Okay. So this was our first kind of alternative approach to an end-to-end optimization. And this is not end-to-end because we are not learning our exploration strategy end-to-end. We're actually using this different strategy for exploring, and then we're learning how to solve the task based on on information we inferred from that exploration. One second alternative approach that I'll talk about is to instead of doing any sort of posterior sampling, we're going to try to explore in a way that tells us information about the dynamics and the reward. And the way that we can do this is if we learn a dynamics model and a reward function for all of the tasks conditioned on our training data, then what we could do is we could try to train an exploration strategy such that this model is accurate. And so once we have this model, we can then kind of train an exploration policy that gets high reward if this model has low error. And so what an approach like this would look like is for each task, you collect some data with your current exploration policy. Then you also collect data with the execution policy, a separate policy that tries to solve the task based on their collected data. And then train your exploration policy with respect to the reward of kind of the negative error of your dynamics model. And then train your execution policy with respect to the goal of solving the tasks. And so note here, the exploration policy and the execution policy have different reward functions. They're optimizing for different things. And this is essentially, this exploration policy is going to try to find things that allow it to predict the reward in the dynamics. And so in this example right here, the dynamics are all the same across all of the tasks. Actually, no, that's not quite right. So the dynamics are actually a little bit different. So the dynamics are different here at the instructions. Because if you kind of move on to the instructions, you're going to see something different for different tasks because the instructions are different for different tasks. And then you also have different rewards. And so what this approach is going to do is it's going to try to learn a model of the dynamics and the reward, and then seek out parts of the state space that allow it to differentiate different tasks. And so then what it's going to do in this case is the exploration policy, once you learn a model based on data, the exploration policy will actually be encouraged to seek out this state because that will help it actually differentiate what the reward is going to be. And so if you also look at the example that we looked at before, where we have these different goals, then it will actually learn a policy that looks like this, where it's essentially trying to learn how to kind of estimate the reward of the task. And a good way to explore to figure out what the reward is to actually go kind of around the circle rather than kind of sampling from the posterior. Cool. Any questions on how this works? Yeah, so this example is different than this one. They're related, but in this case, if you can't actually go around the circle because the dynamics don't let you do that, then you can't take this approach. So the examples are a little bit different here. And so to summarize what's happening here, we are going to learn to predict the dynamics and the reward given the state, action, and our experience. This is just trained with like mean squared error or something like that. Then we'll learn an exploration policy that gets kind of, it gets high reward if the data that it collected helps this model predict well. So it's good if F is able to accurately predict the dynamics and the reward. It also gets kind of negative reward if it's inaccurate. And then you'll also train, this is kind of just, this can be done completely separately from actually solving the tasks. And then this execution policy can in many ways just be trained after the fact in order to try to actually solve the tasks given the training data. And this is just going to be trying to maximize expected reward of this policy. And so this is essentially decoupling exploration from execution, because you can first just train this model and explore so that this model is accurate, and then separately use your experience to actually figure out how to solve the tasks. Yeah?
I can go through, just like the intuition behind the car. That's sort of
Yeah, great question. So the exploration reward, it's essentially set to be the negative error of this model. And the intuition is that if this model is accurate, that means that you've been able to distinguish information about the task. You've been able to predict the dynamics or the reward for that task. And so this is going to be rewarded in cases where you've learned information that helps it distinguish different tasks. And you're going to get a negative reward if this model is inaccurate, if it's not able to predict the dynamics and the reward for the current task. Yeah?
what is like, where did like the state action there say like evaluate the exploration also? Like, is it from like, what like example or two?
Great question. So essentially this reward is, I'll write it out right here. So, not that. So you're going to sample your training data from your exploration policy, and then the reward is going to be evaluated on this training data. So the reward for exploration will be kind of for the state action pairs in this collected experience. What is the negative error, which is f of s a minus r and s prime. So this is the kind of the full equation for the reward. Yeah.
I guess follow up on that is like, there's some risk that like this exploration policy is incentivized sometimes to stay like on something very
Cool, good question. So one issue that might come up is if you, right, great. So if you only evaluate this on the support set, then it might just stay in place and not actually be able to, which is actually bad. And so, yeah, that's interesting. I can't remember actually how they dealt with that problem. I'm guessing that actually it's probably a mix of detrain and, sorry, yes, okay. So this model is conditioned on your training experience. And so you want, so you want your model to be able to predict well based on your training experience. And then this expectation, I think, is actually going to be with respect to states that are sampled from a policy that's solving the task, or something that's actually more broad than just the training experience. Yeah, that's a great correction. So I'll just name that DI. But it's very important that these are the same thing, because this is actually what the model is using to make predictions. Yeah.
Follow-up question about exploration rewards. I don't think it's a good enough for training an exploration policy, because I think it's up to train the word model. So basically I'm thinking, okay, I'm going to introduce another exploration reward with reward the states that kind of surprise the word model. I think that's a better one, a better replacement for this.
So yeah, one downside to this is that you do have to train a dynamics model, and training this might be expensive. You're suggesting that instead of trying to minimize model error, you'll try to learn things that are surprising to the model, that it can't model accurately. I think that that's a reasonable approach. That is actually, people have done that in like standard reinforcement learning. I'm not sure if that would necessarily learn exploration strategies that are targeted for particular tasks. And one thing that's nice about this objective is it is going to try to discover the things that are different among different tasks and use that to solve the task. And that's a good strategy because if you learn about everything that's interesting, there might be like a lot of things that are interesting and surprising, but aren't relevant to the task. And essentially what we want to do when learning exploration strategies is to find things that help us figure out what the task is and ignore things that are irrelevant to the task. So that said, one thing that is potentially bad about this approach is if there are parts of the dynamics that are different across tasks, but irrelevant to solving the task, then it will actually try to seek those out. And so, yeah, essentially if there are a lot of task irrelevant distractors, also if you're in a very complex high-dimensional state space where learning a model is difficult, this sort of approach will be less satisfying. Cool. So overall, these approaches are generally a lot easier to optimize than the end-to-end optimization because the exploration strategy is, like the objective for the exploration strategy is more decoupled from actually learning to solve the task. They're not optimizing the same objective. A lot of them are based on principled strategies for exploration, but the downside is that these approaches can be arbitrarily suboptimal. So, for example, in posterior sampling, we saw that it won't like learn how to read instructions. Likewise, for the second approach, if there are aspects of the dynamics that are different across tasks that are very interesting but are completely irrelevant to solving the task, like maybe there are lots of paintings on the wall that vary across different tasks, then this approach is going to try to explore all of those details, which will not be very useful and will be very, it might spend a lot of time doing that rather than actually learning to differentiate the things that are relevant for solving the task. Cool. And so what I'd like to get to now is an approach that actually tries to decouple these two things without sacrificing optimality. And it turns out it is actually possible to essentially get the best of both worlds, where we're able to explore in a way that is only relevant to the task, and also do so in a way that's very efficient, without having this coupling problem. Cool. So the last solution that we talked about was to try to predict the dynamics and explore in a way that allows you to better predict the dynamics. But do we really have to learn a full dynamics model and a full reward model? The idea that we're going to look at here, the almost final idea, is to label each of your training tasks with a unique identifier. This could just be a one-hot identifier, like you just enumerate all of your training tasks. And then instead of trying to predict the dynamics and the reward, you're going to try to predict this identifier. And so what this will look like in this example is instead of predicting dynamics and reward, we're just going to try to predict what the task identifier is. And this model will be accurate essentially when it finds things that are different among the tasks. And so if the instructions are something that's different in the different environments, then this will encourage the exploration model to find the thing that helps it differentiate between the tasks very quickly. And so that's kind of what the exploration strategy will look like. And so concretely, we're going to train this task identification model. I guess I named it Q. And also train an exploration policy that tries to explore if Q is accurate. And so the exploration policy is trained such that when you sample data from your exploration policy, you're able to accurately predict the task. And then we'll separately train an execution policy that is just conditioned on the task identifier. And this last part should be really easy because this just amounts to solving the task independent of figuring out how to explore for those tasks. And so this is completely decoupled. And then once you do this, then at meta test time, you can explore by collecting data from your exploration policy, then infer what you think the task ID is, and then condition your execution policy on this task identifier. And so one of the things that's really nice about this is now you no longer have to model the dynamics and the rewards. And it should actually encourage it to find things that are different about different environments. And so going back to our objective right here, this will now be something that's trying to predict just the task identifier from your training data. And this is going to be compared to the true task identifier. And then the reward for your exploration policy will be how well it's able to predict the task identifier. And then, so we have these three models. We have something that takes as input. We have our exploration policy, which then outputs your training data. We also have a model that takes training data and predicts mu. And then lastly, a model that takes mu and predicts or solves the task from there. Okay, now I guess, can anyone spot any downsides with this approach? Yeah?
For example, two task IDs are very close to each other, but the real tasks are not very close.
Yeah, so if two of your task identifiers are like very close in value, but in reality they're very different, then this is a problem. If you use a one-hot identifier, this will be better. And then instead of using mean squared error, you could do like cross entropy loss, and that will resolve that issue. Any other thoughts? Yeah?
I have a follow-up question on that. Does the task identifier assume that you've seen that task before? Because if it's like a one-hot vector, then what's your assuming that?
Yeah, so this is essentially the downside, which is that if you give it a new task identifier, if you have like a new task, for example, then it's not going to be able to, like, if this is like your one-hot vectors for all of your training tasks, then it's not going to know how to predict like a one-hot identifier for the new task, and so it won't generalize well to new tasks because you're just using, especially if you're using one-hot identifiers. Yeah.
I don't understand how to solve the problem, because don't we still need to have trajectories that, in this example, how to read and then go and find the correct hallway in order to distinguish between the different tasks? And that was the same problem that we had in previous Stanford. Still needed those trajectories.
Yeah, great question. So the question is, it seems like maybe we still need trajectories that like go read and then solve the task, and maybe this doesn't solve the problem. The reason why this can solve the problem is that for different tasks the instructions are going to look different. And what this exploration policy is going to try to do is it's going to try to be able to discern the task identity from its interactions. And because the instructions look different for different tasks, it can discern what task it's in by just walking to the instructions and stopping there.
Know which task that corresponds.
Yeah, so then the question is, without reward feedback, how does it know which task this corresponds to? By enumerating your task identifiers, this reward doesn't depend on the task reward in any way. It just is looking at whether you're able to predict the task that you're currently in, the environment that you're in. And so it will essentially this exploration policy will get a reward just for being able to predict a task identifier, completely separate from actually being able to solve the task from that identifier.
Okay, so that goes back to like others were saying, where you have to know, like before, what all your task identifiers are.
Yeah, so this is going to assume that you have task identifiers, that you've been able to enumerate all of your training tasks, and you know which training task you're currently exploring in. Yeah?
If you use a non-one-hot task identifier, is that probably going to be hard?
Yeah, so if you use a non-one-hot task identifier, is this better? It is better if you can. In the next couple slides, we'll talk about an approach that will still work even when you have one-hot task identifiers, but it definitely gets a lot better if you have more informative task identifiers. Yeah.
How do you get such non-one-hot task identifiers in practice?
Yeah, so how do you get these task identifiers in practice? It kind of depends on the domain, but if, for example, we're in the kitchen example where the goal is to like cook a meal in different kitchens and you need to find ingredients in different kitchens, then basically whenever you collect experience in a kitchen, you tell it like you're in kitchen 1. And if you're in a different kitchen, you say you're in kitchen 2, or a different kitchen, you're in kitchen 3. And you just need to make sure that you are consistent saying like you're in kitchen 3 when you're actually in kitchen 3. Sorry?
By just telling the particular kitchen, isn't that still one hot?
Oh, sorry. I think I misunderstood your question. You're asking how do you get non-one-hot identifiers? Yeah, so getting non-one-hot identifiers is harder. You would need to be able to like give it features that distinguish the kitchens, for example, that identify like where the like what cabinet are the ingredients in, and what is like what's other information about the environment. Yeah. Yes, and so that's what we'll do on the next slide, is essentially try to learn a better task identifier that isn't one-hot from the one-hot task identifier. Yeah.
But to learn that one-hot identifier, would you need to learn like a linear, we would have like some kind of multi-layered perception on that, probably on like a linear prediction at the end, right? And then we can just take which one of the prediction.
Yeah, maybe I'll just explain. Maybe I'll kind of talk about how we solve this. So essentially, what we're going to do is we're still going to assume that we have these one-hot identifiers, and we're going to try to learn a representation. We're basically going to introduce an additional model that goes from one-hot identifier to our task representation. And so I'm going to erase this stuff. So we're going to have one model that goes from our task identifier, our one-hot task identifier, to a better task representation. We're also going to have a model that goes from this task representation to actually solving the task. So this is our execution policy. And then we're also going to have our exploration policy, and this is going to spit out some data that it explored with. And then we'll have one final model that can try to predict the task from this training data. And instead of predicting the one-hot, it's just going to try to predict our Z. So this will essentially have, this is like 4 different models. This is, we'll refer to as Q because it's trying to infer the task from the data. This is just our execution policy. This is our exploration policy. And then this model right here we'll call capital F. If we can learn these 4 things, then what we can do at meta test time is we will then, we'll take our exploration policy, which will give us data. We'll predict Z from that data, and then we'll plug this into our execution policy. And so at meta test time, we're going to kind of throw away this encoder part. This will just be used during meta training to learn a better task representation. And once we have that, we'll then be able to explore, collect a training data set, get a good task representation, and pass that to our execution policy. So this is kind of a sketch of how things are going to work. And so in particular, there's 2 aspects of meta training. The first part will be learning this first model right here, which is going to both learn how to solve the tasks conditioned on the task ID, and also learn a good representation of the task in the process. And so this will essentially just train a policy condition on one-hots. We're going to bottleneck the representation on this intermediate variable z. The MDP identifier could be a big one-hot vector. It could also be some other descriptive information about the environment. And then this is just doing standard kind of one-hot conditioned reinforcement learning. And then for the second stage, we're going to learn how to explore by trying to recover and be able to predict our z, our task representation. And so this will be trying to train an exploration policy that collects data that allows you to predict what the task variable is. Cool. And so in this first step, like I mentioned, this is basically just going to be trying to maximize the task reward with respect to your execution policy. We're also going to impose a distribution on z like we did before. This is just going to encourage it to throw information and throw out information in the one-hot identifier and learn a representation that's more compressed. And then for the second step, we need to train our exploration policy in order to predict the task representation. While you can do these separately, you can also just train them all at once as well. In practice, it will probably learn the first step before it learns the second step. Yeah.
Without the KL difference determined without the distribution there, would it just learn to just take those, like if our input view was a one-hot encoding for the task, it will just map it to that same, right?
Yeah,
Like
exactly.
an identity mapping.
Yeah, so this could just learn an identity mapping, and by adding the KL divergence and adding noise, we're going to encourage it to not learn the identity mapping and try to compress that representation. Cool. So this is also a decoupled approach in that we're training the execution policy and the exploration policy with different objectives. And we can first train the execution policy and then train the exploration policy. One more detail in terms of training this exploration policy is you could use a reward similar to the reward that we talked about before, which would be to essentially be able, simply try to be able to predict z from your training experience. One detail is that you could do this at the very end of the episode, but it would be nice if our exploration policy got rewards at every single time step. And so what you can do is you can actually give it this reward based on all the data it's collected so far, and do that at every single time step. Now the downside to that is if you do this for the data collected so far, then you're going to start double counting, because if it had if it explored well, like at time step 1, but then did like random stuff after that, then you're still going to be giving it positive reward for that. And so what we'll do in practice is we're going to actually try to measure this per step information gain about z. And the way that we can do this is have the reward correspond to the prediction error, comparing the prediction error up until the current time step and the prediction error up until the previous time step. And this is going to get essentially higher reward if it is able to effectively lower the prediction error from the previous time step to the current time step. And this will essentially give it a more dense reward to say, at this current time step, did you actually help me gain information about what the task variable is? Yeah.
Is that like adding a baseline or?
The question was, is this like adding a baseline? It's not quite like adding a baseline because it's not a constant that you're adding. So it is, it's essentially just trying to prevent double counting. And it's just looking at it. And you can't actually formalize it as information gain. Okay, so this last approach is referred to as DREAM through a somewhat mangled acronym. In terms of trying to get the best of both worlds from this approach, we'd love to get both kind of both a good exploration strategy as well as efficiency from learning. We're running low on time, so I'll go through this pretty quickly, but essentially you can show that the DREAM objective is consistent with end-to-end optimization. And what I mean by this is that kind of in the limit, like as your meta training data kind of goes to infinity, then the expected reward of DREAM is going to be essentially equal to the expected reward of the end-to-end approach. So essentially, as you get more and more meta training data, the solutions will be the same. You'll get the optimal solution in both cases. This is under somewhat mild assumptions. And so, yeah, essentially means in principle you can recover the optimal strategy. You can also do some theoretical analysis on efficiency as well. Doing analysis on efficiency is difficult in general. And so if you look at a more bandit-like setting, I think I don't have time to explain the setup, but essentially you can show that the sample efficiency of an end-to-end approach in orange is very terrible as you make the exploration more difficult, whereas the sample complexity of a DREAM-like approach is much nicer as the exploration becomes more difficult. The dashed lines are showing the theoretical results, and the solid lines are showing the empirical results. And so you see that the theory does seem to be indicative, although it's actually, in practice, it seems to be an even bigger difference. Cool. So to summarize, the end-to-end approaches will in principle lead to the optimal strategy. In practice, it's a pretty challenging optimization. The alternative strategies are a lot easier to optimize, and many of them are fairly principled, but they can also be suboptimal by an arbitrarily large amount. And the decoupled approach that we saw last will lead to the optimal strategy in principle. It's also easy to optimize, so we really get the best of both worlds. It does have this requirement of being able to kind of assign a one-hot identifier to all of your tasks. In practice, this is fairly mild, but it is, it's one thing that it is using in order to get the best of both worlds. You can also empirically compare these different approaches. In this example, different tasks correspond to going to different objects. And the agent starts behind the wall, and it needs to, the optimal thing is to go around the wall to read the sign to figure out the color of the correct object, and then go to the correct object. All of it's from pixel observations and sparse rewards, so it's a pretty challenging problem. And if we look at the average return as a function of meta-training experience, we see that the end-to-end approaches shown in yellow, green, and red all do very poorly because it's really hard to learn exploration and execution together. We see that using something like posterior sampling is able to do better than these approaches, but it cannot learn the optimal exploration strategy because it's going to try to go to objects and get negative rewards when you go to the wrong object. And then lastly, the last approach that we talked about can efficiently learn a good approach, and it also starts to approach the optimal reward for the task. And you can actually look at what the behavior it does, and you can see this is the exploration episode, and it learns to go around the wall and then look at the sign. And the execution policy uses this, the exploration episode infers what the task is and then goes to, it goes to the right object. Cool. So that was the main plan for today. A quick roadmap for the remaining lectures. Next week we'll be talking about offline multitask RL and hierarchical RL. And the following week we'll have some really awesome guest lectures. And the week after that, we'll be talking about lifelong learning and frontiers. You can essentially think of next week as the final reinforcement learning topics. The following week as some lectures on multitask NLP and learned optimizers. And then the last week about learning tasks sequentially, and then some open challenges in the field. The next week and the last week are lectures that will be taught by Karol. And the week in between are guest lectures. And so this is my last lecture for the course. I just wanted to thank everyone for being kind of an engaging student group. And yeah, I really enjoyed teaching everyone.